All right, welcome back, everybody. Today we're going to be continuing our conversation about series, infinite series, and today we're actually going to talk about alternating series and what's called absolute convergence. So there's different kinds of convergence for series, and we're going to talk about conditional convergence versus absolute convergence, and then we're going to get to explore a little bit a really, really interesting theorem called the Riemann rearrangement theorem. So let me get some stuff set up, and let's get started. Okay. All right, there we go. So this is section 11.5. Here's the overview. We're just going to get a definition of alternating series to begin. Then we'll talk about the alternating series test, the alternating series estimation theorem. Then we'll get to absolute versus conditional convergence, and then we'll finish up with the Riemann rearrangement theorem. So here we go. What is an alternating series? Well, maybe not surprisingly, an alternating series is a series whose terms are alternately positive and negative. Alternately positive and negative. So in other words, the terms of the series change sign at every step. How do you get this alternation? You achieve this alternation through an alternating factor, which is something we've seen a few times now. And that's really what it is. So if you have an alternating sequence, there's an alternating factor that's giving you that alternation, all right? So here's a couple easy examples. This is the alternating harmonic series. So it's basically the sum of the reciprocal positive integers. But what we're going to do now is we're going to change the sign of each term at each step. So you see here it's 1 minus 1/2 plus 1/3 minus 1/4 and so on. So that's what we mean by an alternating series. It's alternating between positive and negative. Here's another one. This is that other alternating factor that I mentioned back in section 11.1, cosine n pi. That alternates between -1 and 1 for n integers, I should say, for n and integer. There you go. All right, so here's the alternating series test. And this is a really, really helpful one because if you have an alternating series that satisfies these conditions, it tells you if the series is convergent or not. So here's just a generic alternating series right here. And here are the three conditions that the series needs to satisfy in order for you to apply this theorem. For one, we need the terms to be positive, or really I should say the b sub n terms to be positive. Let me pop this note first. So b sub n is just everything in the summand except the alternating factor. So if you look up here, you've got an alternating factor times bn. So when you're looking at an alternating series, you can kind of push to the side the alternating factor and then look at the rest of the summand right there. So we need the rest of the summand to be positive for all n sufficiently large. We need the sequence of b sub n's to be decreasing, and we need the limit of the b sub n's to be 0. And if you have all three of these conditions, then your alternating series has to be convergent. So it's a really, really nice test. You just have to test three simple hypotheses, and if you've got that, then you know that your series converges. All right, let's look at this one. So let's look at the alternating harmonic series. And again, like I mentioned a moment ago, it's basically just the reciprocals of the positive integers, but you're going to change the sign at every step. And so what I've done is I've rewritten the summand in the form that lets us see what b sub n is. So in this case, b sub n is just 1 over n. So the question is, does this series converge or not? Does it diverge? So this one, I'm going to let you think about it for a minute and ask yourself if you think the series converges or diverges. All right, now say something out loud to yourself. Do you think it converges? Do you think it diverges? If so, what would you do to test it? All right, now try to write down your argument. Write down an argument that you think proves that it converges or diverges. And then we'll go through the argument together. All right, so let's try this one on our own. Well, for one, it is an alternating series. The terms are alternately positive and negative. So maybe the alternating series test can help. Hint, hint, hint. What's b sub n in this case? Well, b sub n is just 1 over n. So what we need to do is we need to analyze b sub n. We need to see if it's positive, decreasing, and converges to 0. But that's not too hard to verify, right? So since 1 over n is always positive. We've got that right off the bat. The other thing is because 1 over n plus 1 is always strictly less than 1 over n, our series is, I'm sorry, this sequence of b sub n's is decreasing. So in other words, the size of these terms is getting smaller as n increases. And then lastly, the limit as n goes to infinity of b sub n is just the limit as n goes to infinity of 1 over n, which is 0. So by the alternating series test, the alternating harmonic series converges. So this is kind of an interesting result because if you remember, the harmonic series itself, just 1 over n, diverged. That was a divergent series. But here, if you alternate the terms, then that's enough of a change to make the series converge, right? So this is why we like investigating these types of series. All it takes is just an alternation applied, and that changes your series from a divergent one to a convergent one, which is a pretty cool result. All right. So that's the basics of the alternating series test. It's really not that difficult. You just got to make sure you have an alternating series and then check these three conditions. And if those are satisfied, you've got convergence. If one of them is not satisfied, then you can't say if it converges or not. So just a reminder about that the direction of implications and what a conjunction means, right? You need all three of these to be able to assert the conclusion of this test. If even one of them is not true, then you can't guarantee the conclusion of the test. So do beware of that little detail. Okay, what's even cooler about alternating series is this thing, the alternating series estimation theorem. So this is a theorem that's literally going to give us a way to estimate the sum of an alternating series, or at least to estimate the error involved with truncating an alternating series. So here we go. Let's say that we have an alternating series that converges, so it's converging to some number, and this alternating series satisfies these three conditions. Then what we know is that the size of the remainder, or the size of the residue, this thing right here, the difference between the sum and the nth partial sum, is no bigger than this term right here, b sub n plus 1. All right, we're going to talk about this for just a minute. I have it laid out nicely here. So what this is saying is that if your alternating series satisfies the conditions of the alternating series test, then the error involved in the approximation that results from truncating the series at the nth term is no bigger than the size of the first neglected term. All right, so ponder that for just a minute. Read that paragraph over, think about it for a moment, and let that kind of sink in. All right, now try to say it out loud to yourself. Try to read this paragraph out loud and see if you can make sense of it in your own words, especially what I mean when I say no greater in size than the first neglected term. And then we'll see an example in a moment. All right, so this other note on this slide for math majors, I recommend that you read the proof of this result on page 805, but I'm going to omit it here because it uses techniques that we've already seen before, in particular when we proved the divergence of the harmonic series. So you can use a similar technique of looking at partial sums and getting this result from that idea or from that investigation. All right, so let's try this. Let's find the sum of the series negative 1 to the n over n factorial, if the sum even exists. And let's get the sum correct to 3 decimal places, right? So I want you all to try this one on your own at the beginning. But one thing I want to mention real quick, we don't even know if the series converges yet. So when you're working with these types of series and a lot of the questions in this chapter, you got to be careful with what you just assume to be true. We don't even know if it's actually convergent. So what we're saying is if it is convergent, then approximate that result to 3 decimal places. All right, so I want you to think about this one for a minute on your own. I'll throw up the thinker there. Okay, now say something out loud to yourself about whether you think it converges or not, maybe what you could use to determine if it converges or not. Wink, wink. Right, and then what I want you to try is just try to prove that it converges or diverges. So start with that. Start with that, and then we'll do the approximation part together. All right, here we go. So let me just say this to begin. I suspect that it will converge because I know that n factorial grows very, very quickly. So 1 over n factorial is probably going to get small very, very quickly. And I suspect that the terms will be small enough that it will converge. Not to mention, we also have this alternating factor involved. So I suspect that adding and subtracting terms in this way is going to lead you to a finite result. But again, no guarantee. Don't take my word for it. Don't take me on faith. Let's actually prove it. All right. So we're going to verify that the series converges using the alternating series test. So first of all, b sub n is just 1 over n factorial. That's always positive, so we're good there. Not to mention the b sub n plus 1 is going to be strictly less than b sub n. And that's really just using the definition of the factorial function. N plus 1 factorial is equal to n plus 1 times n factorial, but this is clearly less than 1 over n factorial. So we have a decreasing sequence. Check. Next thing is that we know that 1 over n factorial is greater than 0, and it's also less than 1 over n. So by the squeeze theorem, because both of the limits of these outer sequences is 0, the limit of the inner sequence must also be 0. So this is a good time to point out how often the squeeze theorem pops up and frankly how quickly you can apply it. You don't want to just run away and say, oh, this thing obviously goes to 0. You should be able to justify it in some kind of rigorous way. And this is a really good way of justifying it, the squeeze theorem. That goes to 0, that goes to 0. This is always in between, so that goes to 0. Okay, so by the alternating series test, the series converges. And now because it satisfies all 3 of these conditions necessary for the alternating series test, we can use the alternating series estimation theorem. So here we go. We're going to compute some of the initial terms. We're going to compute, oh geez, how many did I do? 1, 2, 3, 4, 5, 6, 7, 8. I computed 8 terms. So what I'm doing is I'm just writing out the first 8 terms of the series, the sum, right here. Right. Then I just simplify it a little bit. That becomes 1, this becomes 1, 1/2, 1/6, and so on. All right. And the question really is, how many of these terms do we need in order to guarantee that if we were to chop it off, we would get a result that is correct to 3 decimal places? That's the goal here. That's what we're going for. I do a little bit of clever arithmetic here just to get a look at some size of some numbers. So here, 1 over 5,040 is less than 1 over 5,000, but 1 over 5,000 is equal to 2 over 10,000, which is 0.0002. All right, and this is actually the 7th, or this is B7. This is the 7th term that appears here, or it's this thing right here, I should say. That's what it is. So that's like B sub 7. And what we just found out is that whatever that number is, it's got to be less than 0.0002. All right? So the alternating series estimation theorem says that whatever the error involved is, whatever this error is, it's got to be less than B7, which is less than 0.0002. So an error of less than 0.002 doesn't affect the 3rd decimal place. So we have that our sum is approximately equal to 0.368. And this is accurate to 3 decimal places. Okay. In practice, this is how you can use the alternating series estimation theorem. There's some additional things I want to add to this example. For one, this part right here, simplifying this part, you can use a calculator if you need to when you're like doing the homework or something. These might be difficult to calculate. Same thing with this. So this step that I did right here that I just circled, this is me just using some basic arithmetic to get an idea of the size of B sub 7. But if you have a calculator at hand, you could just use a calculator and see that this is actually gonna work. And what the alternating series estimation theorem says is that if you cut the series off at the 6th term, then the error is going to be no bigger than the size of the seventh term. That's the idea. Uh, my indexing is slightly off when I say it now because this technically starts at 0. So really this is like the eighth term and this is the seventh term, but the idea is the same. If you chop off, if you chop off an alternating series at some point, the error involved will be no bigger than the first thing that you neglected, the first term that you neglected. We can talk more about that during the activity session if you want a little more intuition for it, but that's the basic idea. So once you chop it off, your error is no bigger than the first term that you neglect. All right. Okay, now let's get into some interesting things here. So absolute and conditional convergence. You may be surprised to learn that there's actually different kinds of convergence, and there aren't just these two. There are other types of convergence as well. And there's a whole branch of mathematics dedicated to exploring the convergence of series. We're going to focus on two for now, absolute and conditional, but you're welcome to look up the other versions of convergence. A lot of times people will explore different even ideas of what convergence means and come up with new ideas of convergence. But we'll just stick with these two for now. So a series is called absolutely convergent if the series with the absolute value terms is convergent. So in other words, if you've got a series of a sub n's and you instead look at the series where you take the absolute value of every single term, and you find that this series converges, then the original series is absolutely convergent. Okay. Intuitively, basically, this means make every single term in your series positive and then see what you get. And if you're able to make every term in your series positive and you still have a convergent series, then your series is absolutely convergent. So it's a powerful form of convergence. Now, if this property does not hold, then what we say is that your series is conditionally convergent. So a series is conditionally convergent if it converges, but not absolutely. Not absolutely. All right, let's look at an example to get some intuition here. This series right here is an absolutely convergent series. And the way that we can tell is we take the absolute value of the summand and we look at the resulting series and see what that series does. Well, this series is just a p series and it converges by the p-test because p is greater than 2. I'm sorry, p is greater than 1. In this case, it's equal to 2. All right, so because this series converges, that means this series converges, which means this series is absolutely convergent. And that's the claim right there. Yeah, there we go. Wait, yeah, there we go. So that was it. So this series does converge. I should add that right there. This series converges absolutely. Now let's compare this to the alternating harmonic series. So the alternating harmonic series we know converges. We proved that just a couple minutes ago using the alternating series test, right? So this series converges. Now let's look at the absolute value series. We're going to take the absolute value of all the terms, and when we do that, we get the series of 1 over n. So what we get is we get the harmonic series again, which we know diverges. So this series converges, but this series diverges. So that means that the alternating harmonic series converges conditionally, not absolutely, but conditionally. And we will we will see why we use this word conditional to describe this behavior in just a couple minutes. Okay. Easy result that follows from this, not surprisingly, if your series is absolutely convergent, then it is convergent. Not too hard to believe that's true. It's an easy proof. If you would like to try to do the proof, I encourage you to try it out. If your series is absolutely convergent, then it is convergent. All right, now, here is one that I want you all to try on your own at home. I want you to determine if the series given here is absolutely convergent, conditionally convergent, or divergent. It takes a couple of steps, so you might have to take a couple of minutes to do it, but first think about how you might approach it. Okay. And then say something out loud to yourself about how you might try to prove one of these three. What are you going to try first? Okay, now try to carefully write out your argument. Remember to use complete sentences, use proper grammar, just try to write things out very carefully in a neat, organized way, explaining in detail why you think one or the other is true. All right, now let's do this one together. Let's see if it's absolutely convergent. And then do I have a note about this here? I'll come back and talk about it in just a minute. But let's see if it's absolutely convergent first, and maybe we'll get lucky. So what we're going to do is we're going to take the absolute value of the and we're going to look at the resulting series. So absolute value of n squared is just n squared, but cosine could be negative, cosine goes between -1 and 1, right? It could be any value between -1 and 1. So we still have an absolute value on the numerator there. So now we have a new series to investigate, and this is the new series we're going to investigate. Maybe you can kind of see what we're going to use to determine convergence, uh, but let's go through it together. We know that the size of cosine n is less than or equal to 1 by the definition of cosine. And so that means that this thing is always less than or equal to 1 over n squared. Now, the series 1 over n squared converges by the p-test. It's a p-series. Therefore, we know that this series converges by the direct comparison test. And as a result, our original series converges absolutely by the definition of absolute convergence. There you go. And that's how the arguments go. Again, it's really just a lot of comparisons. It's a lot of inequalities, but it's sentences. There's very little calculation, almost no calculation involved, right? It's really just kind of explaining why something is true. Uh, Before we get to the Riemann rearrangement theorem, which is next, I wanted to make a note, or at least make a comment about a problem like this. Um, if we attempted to see if this thing was absolutely convergent and we found out that it is not absolutely convergent, that doesn't necessarily mean that the original series does not converge. It just means that it doesn't converge absolutely. So if you decide to make the initial choice to test for absolute convergence and you find that it's not absolutely convergent, that doesn't mean you can just dust your hands off and walk away and be like, oh, the series diverges. No, 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 that's not true. All you've shown is that it's not absolutely convergent. So now you need to go back to your original series and reevaluate it and see if it's conditionally convergent, because it might be. It might be, right? For example, the alternating harmonic series, that's not absolutely convergent, but it is conditionally convergent. So beware. We can talk more about that later too. All right, but now let's talk about the Riemann rearrangement theorem and get some and see a really, really bizarre result. Here we go. It turns out that the difference between convergence, absolute convergence, and conditional convergence can be very staggering. In a certain sense, conditional convergence is not worth very much, although conditionally convergent series are not to be completely ignored. Um, you'll see what I mean in just a moment here, but absolute convergence is really what you want because absolute convergence lets you do a lot more than conditional convergence. So this is the big rub. This is the issue here. If a series is conditionally convergent, then we can actually prove validly that it converges to any number you'd like, or even positive infinity, or negative infinity, or you can show that it doesn't converge or diverge to any number whatsoever. So conditional convergence is a very, very fragile form of convergence because it basically means it does converge under certain conditions. But if you violate those conditions, then you can say that this series adds up to anything you want, anything you want. And this is why, like I say at the bottom here, a plane with infinity has to be done with care and deliberation. You got to be careful when you're working with infinite series, and you got to make sense of the definitions and make sense of the theorems because it's very easy to assume something true that actually is not true at all. So one of the issues here is that results that hold for finite sums, in particular stuff like commutativity, doesn't necessarily hold for infinite sums. This is a bit of a flashback to section 11.2 when we first talked about series. And there were a couple very, very quick theorems that I blew through and was like, oh, if you move the terms around in a finite sum, then you still get the same result. That's just commutativity. Well, it turns out that commutativity doesn't always hold for infinite sums. And we're going to see this in just a moment here. All right, so this is where the Riemann rearrangement theorem comes in to clarify everything. This is the actual statement of the theorem. So suppose that this A sub n is a sequence of real numbers and that this series is conditionally convergent. Let m be any real number you want. Then what this theorem says is that there exists a permutation sigma of n such that if you permute the terms a sub n, you can get them to add up to that number m that you chose. So let me pause here for just a minute and try to clarify some of the notation here. Remember that this, let me use a different pen here. Remember that this little subscript is an index. It's an index that indexes the sequence, the terms of your sequence that you're adding up. So A1 is the first term, A2 is the second term, A3 is the third term, and so on. What this bit is saying is, hey, if you take those numbers 1, 2, 3, 4, 5, and you move them all around so that maybe they go like 3, 10, 1, 2, 9, 11, 15, 29, then that's what a permutation is. So that's what this is saying here. This is saying if you change the order of the terms, all right, this is what you can do. And what's really interesting is this theorem is saying that you get to pick. You get to pick the number that you want the series to add up to. And what this says is that there exists a permutation of those terms that will get your series to add up to that number. Weird, weird stuff. This is one where I've got to throw up the thinker again, and you just got to sit there and like ponder it for a minute. Like, wait, what? Wait, ponder it for just a minute. Okay, now let's finish the statement of the theorem. That was just the first part of the theorem. It also says this. It also says this. There's another permutation, tau of n, such that if you permute the terms in this way, you can get the series to actually diverge. You can get the series to be equal to infinity. You could also get it to diverge to negative infinity. In other words, there's a permutation that makes it converge, or sorry, makes it diverge to negative infinity. And there's even a permutation that makes the result fail to approach any limit. So conditional convergence is a very fragile form of convergence. It's basically saying, hey, it'll converge to something. Just don't rearrange anything. Don't move anything around and it'll converge. But also, if you have something else that you want it to converge to, rearrange the pieces a little bit and it'll converge to that. Weird, huh? Very weird stuff. Okay. Um, yes, so we're going to omit the proof of that here. It's a fascinating theorem. You can read the proof on Wikipedia. The proof is actually not above the ability of anybody in this class. You could read it and understand it if you read it carefully and walk through it slowly enough. But instead, what we're going to do is we're going to demonstrate the conclusion. We're going to show that we can get the alternating harmonic series to add up to two different things just by rearranging the terms a little bit. All right? So we haven't proven this yet. I forget which section we prove it in. I think it's 11.9. I think it's 11.9. But it turns out that the alternating harmonic series converges to the natural log of 2, ln of 2. Funny enough. We'll prove it later. So for now, you're going to have to, unfortunately, take my word for it. So if you don't rearrange the terms, if you literally just do 1 minus a half plus a third minus a fourth plus a fifth, dot, 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 it'll add up to the number ln of 2. Now, we're going to do something kind of bizarre. We're also going to show that it converges to half of that value with rearrangement. So we're going to rearrange the terms a little bit, and we're going to show that when you do that, it adds up to half of ln of 2. So here we go. All right, here's the clever bit. So this we're taking from a future result. ln of 2 is equal to this series. This series is equal to this by definition. That's what this little colon equal sign means. That means by definition, this infinite series is this right here. Right? So then what I did was I moved some of the pieces around. So this is listing out the pieces in the original order. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, right? Now we're going to move some things around. So you'll notice that I rearranged a bit here. So 1/2, 1/2. I switched the order of 1/3 and 1/4. And then I switched the order of, oh, where is it? Well, 1/6, 1/5, and 1/8. So what I'm doing is I'm kind of moving all the pieces around, right? And I'm doing it in an intentional way. Oops, wrong highlight. I'm doing it in an intentional way because we're going to get this, and then we're going to get this, and then we're going to get this, and so on, and so on. And I kind of emphasize that right here in this step. So now we're going to emphasize 1 minus 1/2, which is a half. 1/3 minus 1/6, which is 1/6. 1/5 minus 1/10, which is 1/10, and so on and so on. And when you do that, what you get is this series. And take a look at this series carefully for a minute. It's 1/2 minus 1/4 plus 1/6 minus 1/8 plus 1/10 minus 1/12, and so on, and so on, and so on, and so on. But you notice all of these are even numbers, right? So what we can do is we can factor out 1/2 from this infinite series. We can factor out a factor of 1/2 from every single term of this series. And when we do that, what we get is this. We get 1/2 times 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. But hey, wait a minute. Wait a minute. This right here, that's literally the alternating harmonic series again. That's this thing. Oops. That's this thing right here. So what's in parentheses here is equal to the harmonic series, the alternating harmonic series, and we've got half of it now. So what we just showed is that ln of 2 is equal to half of ln of 2. What? What is going on? What is going on here? All sorts of craziness going on, right? Well, there's a lot going on here. There's really a lot going on here. The important thing here is how we defined infinite series, and we're going to look at this in just a minute. We defined them in a very particular way. That's what I say on this slide right here. We defined them to be the limit of the sequence of partial sums. So this is actually how we define these things way back in section 11.2. An infinite series is defined as the limit of the partial sums. But take a look at this. The partial sum, if you write it out in its expanded form, looks like this. A1 plus A2 plus A3, all the way up to AN, right? Well, consider this for a minute. If you instead were moving all of these pieces around and putting them in a different order, that's going to change the value of the partial sum. And if you're changing the value of the partial sum, that can change the value of the limit of the sequence of the partial sums. And so what happens is you get a different result. You get a different result. Yeah. So if you rearrange the pieces, it means that you're altering the sum if you have a conditionally convergent series. So what's the moral of the story here? The moral of the story here is that that absolute convergence is really what you want. If you can get absolute convergence, it's like, if you've got absolute convergence, you can move things around, you can factor things out, you can push all of a set of terms to the beginning and the set of terms at the beginning to the end. You can do everything that you want to do with absolutely convergent series. With conditionally convergent series, it's touchy. It's touchy. All right. On that note, let's play. So let's explore these ideas again during activity. That's pretty much it. These are some really important ideas. We really like absolute convergence. I know I have to deal with absolute convergence a lot in my research. There are other types of convergence, so if you are interested, please look them up. You might be interested to see. One example I can remember off the top of my head is the series 1 minus 1 plus 1 minus 1 plus 1 minus 1, there's a way to talk about what that series could add up to. You can make that a little more intuitive by changing the convergence that you're speaking of. All right. Okay. I'll stop rambling. Thank you all for listening, and I will see you next time.